Hi, can you hear me? Good. Well, first thing first, I have to remind you that you need to find a place where to sit. We are not allowed to stand for safety reasons, so that's the first message. And, well, beside that, we can get started. My name is Federico Tomassetti. I'm a language engineer. And today, we are going to talk about building languages using Kotlin. So, what we are going to see in this talk? In this talk, we are going to describe the general process that we can follow to create a new language that we can use in practice. We are going to evaluate the effort needed for each different phase of this process. And we are going to discuss how Kotlin can make our life of language designers easier. Now, there are also things that we will not be able to see during this talk. So we will not have the time to go very deep into the technical details and see every single line of code of the implementation. However, at the end of the talk, I will share with you all the source code that I used to build some simple examples. Also, unfortunately, we do not have the time to discuss language design. That will be a huge topic per se. But if you're interested into this topic, I will share with you at the end a list of articles and things that you can look up. Now, before starting building a languages, could make sense to ask ourselves, why should we build languages, right? And I think that in order to answer that, we need to consider there are different kinds of languages. As software developers, we naturally think about general-purpose languages like C#, Python, Java, languages we use every day and we can use to solve every sort of problems. Now, there are reasons to build new general-purpose languages. For example, if you want to experiment with new paradigms or suggest substantial improvement to existing programming paradigm. That could be, for example, the idea behind a language like Haskell. Sometimes it just makes sense to create a language that has better compromises, and while it's not revolutionary, it makes our life of developer easier. So that seems to me the idea behind a language like Kotlin. Another very good reason to build a programming language, in my opinion, is to learn about languages, how languages work, because I think that this kind of experience can improve the way we program and we can provide a better understanding of how compilers are implemented. And also, you can build a language just because it's a lot of fun and you can brag about that with your friends. Well, it really depends on the friends you have. But, you know, with me, it will work. But I think it's important to consider there are other kinds of languages that we sometimes don't consider. And in particular, there are domain-specific languages that I think are very important. Now, I'm talking about real domain-specific languages. Unfortunately, the term is used to indicate very different things, internal DSLs and external DSLs. And internal DSLs are, you know, when someone tries to bend the nature of the language, like Ruby, and give you the impression you're using another language while you're still writing legal Ruby code. I'm not very interested into this. I don't think they're as relevant as external DSLs. Instead, external DSLs are proper languages that are built to support a limited set of tasks. For example, we are all familiar with languages like HTML, that is a language that I can use to describe a document, or VHDL, that is a language that I can use to describe a circuit, and the compiler will generate the physical layout of the circuit for me, or SQL, that I can use to describe query on a database. And there are many of those DSLs, like dot, that I can use to describe a graph, and the compiler will produce for me an image resulting from this graph. Or LaTeX, that, again, I can use to describe a document and obtain a document in result. Now, these are well-known DSLs, and these are horizontal DSLs. So DSLs that perform one task can be used across different industries. There are also DSLs for specific industries, but the problem with that is they are typically not publicly available. So it's difficult to provide examples that I'm allowed to share. I want just to say that in my experience with specific DSLs built for specific organization, I've seen in some contexts huge increment in productivity, and this is, I think, it's a very good reason to consider building a DSL. But they're also important because they support the communication with domain experts. Suppose that you have to write some medical companion software. Now, when you are going to write that software, you will need to communicate with medical doctors. At least I hope that you are trying to involve medical doctors and not do your own thing. And if you have a DSL that is high level enough that medical doctors can understand, it can really help the communication and improve the way that you collect feedback. Similarly, you could build some payroll system. You need to involve accountants, or maybe you're writing the software controlling some machinery. You want to involve mechanical engineers. So DSLs allow you to involve different kind of domain experts in the development, and I think this is a huge advantage. But no matter what kind of language you want to build, a general purpose language or a DSL, you can follow this plan. And the idea is that you start by defining the grammar, so basically how your language will look like to the user. Then you describe the model, so which kind of information your language needs to capture. Then you perform the validation, so you verify that the user have written everything correctly and accordingly to the rules you have defined for your language. Once you have done that, you need to do something with the information that you've captured. And you have different alternatives. In this presentation, we are considering the possibility of writing an interpreter or a JVM compiler on an LLVM compiler. And this last one can be used to generate native executables. Now, this is the bare minimum that you need to have a language that works. But in practice, you typically want to build additional tools like an editor. Well, it's a good idea to build an editor and not force your users to just open Notepad. And other tools like, for example, a simulator can really improve the productivity of your users. So in this presentation, I'm referring to this very simple language that I developed just for the presentation. It's a language that we can use to describe function and simple statements like print statements, variable declaration, and I will share the code of the implementation of this language with its own very simple editor. Of course, this one is a very limited language, but I think that it also represents the core of functionalities that you could reuse in many different other languages that are more evolved and more complex. Now, to bring this language to life, we need to start by defining the grammar of this language, right? So the idea of the grammar is that it will support us to go from the code to a list of tokens to building constructs representing the information in your language. Now, the code is written by the user, and it's basically a big string spanning multiple lines. The first thing that we do to examine this big string is to split it into single tokens. So we are going to recognize the role of each single element present in the code and attribute to it a role. For example, I can recognize that the word fun corresponds to a keyword. The double is an identifier. I can recognize left parentheses and right parentheses, left braces and right braces, or the number 2 is an integer literal, and so on. Once I have decomposed my test in single tokens, I need to recompose it again by recognizing that some sequences of tokens has a particular meaning. So in this context, when I find the sequence integer literal, mul operator, and ID, I recognize this as a multiplication. Or when I recognize int and ID in the context in which they're used, they correspond to a parameter declaration. And there is another example of a variable declaration. Now, to implement this, I typically use a tool that is called Antler. And I use it to implement both the lexer, that is the part that goes from the code to the list of tokens, and the parser, that is the part that recomposes the tokens into constructs. Now, you can see in the right corner a small rectangle with a number of lines. What I've done is I've implemented a few simple languages, 3, and I verified how many lines it took me to implement each phase. Of course, they're very simple languages, and the number of lines of code is not a wonderful metric, but the idea is just to give you a rough idea of the effort needed for each step, and also to compare the relative difficulty of the different steps. So defining a lexer is quite simple, and we can see a part of the lexer definition or the language I wrote for this presentation. And we can see that basically we have a token definition and the corresponding regular expression. So I don't know, for example, the token of type WS, that stands for white space, is defined as a sequence of a space and a tab, I mean, any number of spaces and tabs. Or we have a bunch of keywords that are defined as static strings. So it's, when we meet that string, that particular string, we recognize the corresponding keywords. Or we can have things more complicated, like IDs. So in this case, we say that an ID can start with any number of underscores, then a lowercase letter, and then any number of lowercase letter, uppercase letter, numbers, and underscores. For the second part, defining a parser, and also in this case, you can see it, for a reasonably simple language, it takes 50 lines or less. What we do is we define each single construct in terms of other constants or single tokens. We start by saying that an entire file of our language, the language is called minicalc because it permits to do calculations. A file of this language is defined as a list of lines, and a line is nothing else than a statement followed by the new line or the end of file. A statement can be of different type, an input declaration, variable declaration, assignment, and so on, while a function declaration is the keyword fun, followed by an identifier that plays the role of the name of the function, and between parentheses I have the parameters definition. So you can see that I define constants in terms of other constants or single tokens. So it's quite intuitive, I think. Now, we have defined how to recognize the construct that the user wrote. But at this point, what we want to do is to translate this information in a form that is easier to process, that can support better the following steps, the validation, interpretation, compilation, and so on. So what I do is typically using data classes. That is a very simple feature of Kotlin that I like a lot, because it permits me to define the structure of my data in a very concise and declarative way. So in this case, for example, I'm saying that a variable declaration needs to contain a name, the value, so an initial value that I assign to this variable, and a position. For each element, I will need the position in order to communicate with the user. So later, for example, I can say to the user that there is a problem with a variable declaration at line 10. So I need to keep this information. In this case, I'm also saying that a variable declaration is a statement. It is a declaration of a value. In this language, we have variables and inputs. Inputs are like configuration parameters that the user needs to specify when he starts the application. Another data class that we have is assignment. In this case, we say that an assignment needs to have a reference to a value, the value being assigned, and an expression specifying the value to assign to such to such variable or input. We can do slightly more complex things. For example, this is how I define minicalc file. I say that it contains a list of statements, but I also have some derived properties. So I say, for example, that the inputs are all those statements that are instances of input declaration. Or that my top-level function are all the statements that represent function declaration. In this case, I say top-level function because this simple language permits to have function inside other functions. Now, once I've expressed the structure of the data that I want to have by using data classes, I still need to map what I have obtained from the parser into the models that I've just defined. And I call this operation mapping. And basically, I typically add extension methods to classes generated by Antler, and we can recognize them because they end with the word context. And these extension methods have the goal of generating corresponding element in my model, so using my data classes. In this example, in the grammar, I've defined a binary operation as an expression, an operator, and another expression. And in the grammar, I just needed the concept of binary operation, and I didn't need anything more detailed, because from the point of view of the parser, all these binary operations have the same structure. They look the same, so it's not needed to have more details. While from the point of view of the model, and to support the following operations, I want to distinguish between all these operations because I want to treat an addition or a multiplication in a very different way. So what I do in this case is I take a binary operation, I look the when operator to look at the test of the operator, and depending on the operator, I instantiate different instances of my data classes. Now, this is one case in which we do some elaboration in translating the output of the parser into my model. In many other cases, the mapping is one-to-one, so we don't need much adaptation. For this reason, typically the mapping is something that can be done in very few lines. In these examples that I built, is less than 100 lines. OK, so we have recognized what the user has written. We have translated it into our model in a form that is easy for us to process. Now we need to verify that what the user has written is actually correct. It's correct from the semantic point of view. Now, to perform the validation, we have to consider these points. Now, all the information is being translated into the model. Our model is composed by the instances of the data classes that we have briefly seen. And we also to consider that the model is a tree. So we have one node that represents the entire file. And from this node, we can reach all the other smaller elements. For example, for the node representing the entire files, we can reach all the top-level statements. These top-level statements could be, for example, function declaration. Inside function declaration, we have parameter declaration. We have other statements that correspond to the body of the function. Inside those statements, we have expression. Expression can contain smaller expression. For example, if you have the expression 1 plus 2, 1 and 2 are smaller expression, but also 1 plus 2 per se is an expression containing the two smaller expressions. So the model is a tree, and basically performing validation just means to navigate the trees and verify that properties are verified on this tree. So the way that we can do that is simply define a couple of operations on node itself. Every single instance of our data classes implements node directly or indirectly. So the first operation we can define is the InProcess. It takes a function and apply this function on the node itself. Then by using reflection, we can find all the properties of our node and iterate on this by calling process on all the elements containing to these properties, with the exclusion of derived properties. If you remember when we have seen the example of the minicalc file, it contains a list of statements, but it also contains some derived properties like top-level functions. Now, a function in that case would appear both in the list of statements and into the list of top-level functions. Because we don't want to navigate two nodes twice, we exclude all the derived properties. Now, process so permits us to specify a function to be executed on every single node of the tree. But very frequently, we want just to execute a certain operation of nodes of a certain type. So for this reason, we specify the extension method specific process that takes, again, an operation to be executed, but also a class. In this case, basically, we'll execute the operation only on the instances of the specified class. This is how we can use this property, these methods in practice. In this case, we specify a call to specific process, and we want to catch all the variable declaration. And for all the variable declaration, we want to verify if we have already encountered a variable with that name. If that is the case, we want to trigger an error. Otherwise, we want to record this name as a name that is already being used. Now, this is a naive example because this doesn't allow to have two variables with the same name in two different functions. So maybe you want to change that in your languages. But the idea is just to give you an idea of a possible usage of specific process. Or for examples, we could want to verify that all the assignments are correct. So we could want to verify that for each assignment, I'm assigning always a value that is compatible with the type of the variable. For example, I want to prevent the user to assign a string value to a variable of type int. So this is how I can define this rule, again, using specific process. So far, there are some characteristics of Kotlin that, in my opinion, made our life easier. First of all, we have data classes and the possibility to specify custom properties. So it permits to define very concisely the shape of the information that we want to process. We have method extension and the when operator that were very useful when specifying the mapping between the output of the parser and the model. We have the possibility of specifying the validation very easily by defining process and specific process to navigate the tree, and by using lambdas to specify the custom logic that we want to use for each single check. And another characteristic that I really appreciate is the usage of extension methods, because it permits me to organize the application by different aspects. Now, in a language like Java, I will tend to have big classes where a single class defines the structure of the data, but also the validation rules or operations that are needed to support the interpreter, the compiler, and so on. But because I have extension methods in Kotlin, I tend to have one file where I define the model and just define data classes with no logic at all, so very simple and concise. Then I have another file where I define validation, other files where I will define the compiler and the interpreter. And so I can separate the things by different aspects. So each aspect in one or more separate files. Okay, at this point that we have recognized what the user has defined, that we have verified it's correct, we need to do something with it. So we need to implement one of these three options. Now, we could implement an interpreter that is basically a program that navigates my model. Model is a tree. And depending on what it encounters, it does something. This something could be evaluating an expression, or adding a new element into a symbol table, or printing something into the screen. Or I could define a JVM compiler. We can consider a compiler as a special case of an interpreter, because also the compiler will navigate the tree and do something. But this do something will correspond to emit some JVM bytecode. Very similarly, I can have an LLVM compiler that, again, will navigate the model and generate, in this case, LLVM bitcode that I can use to generate native executables. So in the next 10 minutes, I'm not going to teach you how to write an interpreter, a JVM compiler, and an LLVM compiler, because that would be quite a challenge. I just want to give you a rough idea of the effort needed. Now, the interpreter is the simplest option that we can have. We can build an interpreter for a simple language supporting the common expressions, so the mathematical expression, variable, assignments, and so on, with slightly more than 100 lines. So it's something quite simple. And basically, an interpreter needs to do two things. First, executing statements, and two, evaluating expression. Now, in this case, we are looking how we can execute statement. We can see that if we have an expression statement, well, we just need to evaluate the expression inside the expression statement. And this is something that is important to do even if we throw away the result, because expressions could have side effects. For example, if I invoke a function, inside this function there is a print statement, this is a side effect that I need to consider. Then, when I need a statement corresponding to a variable declaration, what I do is to evaluate the initial value assigned to such variable, take the result of the evaluation, and insert it into the symbol table associated with the name of the variable. So the symbol table is basically a map. A print statement, well, I just evaluate the parameter of the print statements, and then I print the result. An assignment is very similar to a variable declaration. The only difference is that when I have an assignment, I need to update an entry in the symbol table instead of add a new entry in the symbol table. Also, a function declaration needs to write down the definition of the function that I've encountered and associate it with the name of such function, so that later someone called this function, I know which statements to execute. Now, the other task of an interpreter is evaluating expression. We can see how we can evaluate some of the expressions. So we have things like integer literal and decimal literals. They are quite simple because they carry with them the value. So if I encounter the value 1 in the code, well, the result of evaluating 1 is 1 itself. String literal are a bit more complex in this language because we support interpolated strings, so we can have something like hi $name, so we need to evaluate all the different parts, the constant part and the variable parts, and then concatenate them. While if I have a value reference, so for example in an expression like foo plus 2, foo will be a value reference, and to find the value, I just need to read into the symbol table into the corresponding entry. So just looking up the value into the symbol table. Well, if I have something like a sum expression, things are a bit more complicated because I need to evaluate the different portion, the left expression and the right expression, and then I need to do something different depending on the type of the left expression. So if on the left I encounter an int, I expect also on the right to have an int, and I want to perform an addition of integer. While if on the left I encounter a double value, on the right I also expect a double value, and I will sum these two double values. If on the left I encounter a string, no matter what I have on the right, I will convert it into a string, and then I will have a string concatenation. Now, when I say I expect to find on the right an int, or I expect to find on the right a double, it's not because I really trust our user to not commit errors, but it's because these are the kind of things I will verify and enforce during the validation process. So when I implement the validation, I need to think about the work that I need to do later and prepare the field so that I can avoid having these checks later in the interpreter. Now, writing a JVM compiler for the examples that I wrote proved to be 2 or 3 times more complex than writing an interpreter. Now, to understand how a JVM compiler works, the first thing that we need to consider is that the JVM is a stack-based machine. So the idea is that when you need to perform an operation, you take the parameters and you put those parameters into the stack, and then you invoke the operation. The operation will take the parameters out of the stack, calculate the results, and put the results back into the stack. Now, if I want to evaluate an integer literal or a decimal literal, I will just push the corresponding value, so the corresponding constant, into the stack. That's it. While if I want to evaluate a value reference, what I need to do is to use an operation that take the values out of the symbol table of the JVM and put this value on top of the stack. Now, when I do an operation like a multiplication, what I do is to invoke the parameters, so push the parameters, so I will push the left value and the right value, and then depending on the type of the types involved, so if I'm multiplying integers, I will use imul, or if I'm multiplying doubles, I will use dmul. So it's important to consider that there are different instructions for different types of mathematical operation in the JVM. Now, an LLVM compiler is even more complex than a JVM compiler, at least in my experience. So we can expect that it takes like 50% more code than the JVM compiler. And it's also very different in nature, because while the JVM compiler is based on a stack-based approach, the LLVM compiler is instead a register-based machine. So the behavior is very different. For example, when I need to evaluate a value reference on the LLVM, what I will do is reading a value out of symbol table and give to it and put it in a register and record the name of this register to later use it. When I have an integer literal or a decimal literal, these are immediate values that I can use directly into more complex expressions. An example of more complex expression are in this slide. You can see that we can consider the first one, the float division. The code that I need to generate for a float division will be the keyword fdiv, followed by the type. So I use it to specify if I am using single precision or double precision in this case, because I'm operating on floating point numbers. Then I will specify the code corresponding to the left operator and the right operator. In the case of constants, it will be the immediate value, while in the case of references, it will be the name of the register where I put the value that I read from the symbol table. So it's a bit tricky, and it's very different in nature from the JVM compiler. Yeah, we can skip that. Now, to summarize the three different approaches, when I build an interpreter, I do not need any framework. What I do is performing simple operation, and basically everything I do involves using the symbol table. Now, the symbol table is a simple class that we can define ourselves. It's basically a map. We can have annotated symbol tables, so to represent annotated scopes. So it could be slightly more complex, but it's not too difficult. Writing a JVM compiler is quite more complex because it requires to familiarize with the JVM internals and to understand this stack-based approach, so putting the values into the stack and later invoke the operation. But you can use a library that is called ASM that is really simplify your life and hides some technical details, like, for example, things about the class pool that you do not need to know in details to be able to write a JVM compiler. The things that I found the hardest is writing compiler for the LLVM. And I found, at least for me, the Java binding is very complicated. So what I've done is writing a simple library called KLLVM that I use just to generate the test representation of bitcode. And then I use a tool from the LLVM to compile it and obtain native executables. Now, another aspect to consider that will require also some work is building an editor, and can really make the difference for the usability of your language. Now, the good news is that we can reuse a lot of the work we have already done, because an editor needs to show syntax error, and the syntax errors are calculated for us by the parser. The parser will be able to tell us that we cannot use a certain keyword in a certain position. Then we need to specify semantic errors, like the fact that the user defined twice a variable with the same name. But we have defined the validation, and the validation gives us errors referring to nodes. For each node, we have the position, so we can show these semantic errors into the editor. Syntax highlighting is also something that we can get for free simply by considering the output of the lexer. The lexer has identified the different kind of tokens. Basically, what we do is to associate different colors to different kind of tokens, and we can have syntax highlighting for free. The part that typically requires most work is the autocompletion, because on one end, we need to somehow reuse the grammar to understand that in a certain position, we can expect to follow a certain keyword or an operator or an identifier. But the problem is that it's not always easy to understand which symbol are available in a certain context, so which variables I can refer in a certain position. For this, I need to specify scoping rules, and so it requires some extra work. I cannot obtain this for free like the other features. And simulator in general, well, it mostly applies to the case in which you build domain-specific languages, but in my experience, building a simulator can really help the user to play with the language in an easy way, and so provide feedback more quickly. That is, I think, one of the most important aspects. And a simulator can basically wrap an interpreter and add in some extra features. So, for example, build some DSLs to represent medical companion software in the simulator, extra features to support manipulation of time, so that the doctor could press a button to say, let's skip 1 day or 2 days, and then pretend the user insert this value, and let's see what happened. So in that case, the simulator really made a difference. Now, I want just to approach the conclusion by saying that Kotlin has changed the way that I build languages, because before I started using Kotlin to building languages, I was forced to use what are called language workbenches. There are special tools that we can use to create languages. For examples, we have the Eclipse Xtest or the JetBrains metaprogramming systems. Those are very great tools, but the problem is that they are not flexible enough to be used in all possible situations. So by writing my own infrastructure from scratch in Kotlin, I have the maximum amount of flexibility, and I can accommodate all the different requirements that the user can have. And the main difference into using Kotlin with respect to just writing in Java, for me, was the productivity. I was surprised to find out that I can build very simple languages with a parser, an interpreter, and an editor in around 1,000 lines of code. I cannot imagine be able to do that in Java. And here I summarized the effort needed to implement all the different phases. Of course, those are very simple languages, so if you are going to build a general purpose language like C++, probably it's taking 10 times the effort, if not 100 times the effort. But still, I think it's useful to understand the relative difficulty of the different steps. And what I've experienced is that writing a compiler is much more complex for me than writing an interpreter, and is the most complex part of our infrastructure. And the second most complex part is the editor. In particular, defining the autocompletion can be quite tricky. While all the other aspects, so writing a lexer, a parser, the model, the mapping between the parser and the model, and the validation are relatively simple. So that's the end. So I prepare a page where you can find all the code, the slides, a list of articles and tutorials. And I also wrote a book on this approach. So if you want to take a look, you will also find a coupon for that book on this page. And so that's it. Thank you. And now if someone has questions. Okay. So the microphone should reach you. Yeah.
So what did you use to build the editor with only 300 lines?
Well, for the editor, I actually wrote a simple framework myself, reusing some libraries that were existing. The framework is called Canvas with a K, like Kotlin. And so I just put the common parts that I tend to use in all the editors in one place, so that I can just, every time just customize with the parts that are different, and saves me quite some time.
At what point in the validation do you throw the error? Like, is it down the stack or up the stack?
I just collect all the errors, and then at the end, I typically show all of them into the editor. So I can show the syntax error and the semantic errors at the same time.
Sure. So the beginning stage, so it was in I think Antler, right? The Lexer and the parser, right? Did you actually need that, like, to go to the next page where you were writing Kotlin code? Because I wasn't quite sure, because I've seen that output of Yak or whatever it is. I just don't see how that would relate to the Kotlin part.
Well, I like to use Antler because Antler permits to define very declaratively the grammar. And I can reuse this definition also during the auto-completion phase. While if I wrote the parser by myself, it would be, in my opinion, more complicated. Also, Antler can generate code for many different languages, so I can reuse the same parser, for example, in the browser, because it can generate a JavaScript parser. So that's why I really like to use Antler.
Have you encountered any difficulties when handling operator precedents with Antler?
No, Antler is quite good in that respect. Basically, you just use the order in which you define the different alternatives. So you don't need, to write these extra rules just to accommodate the precedence. With Antler 4, it does that for you, and it leads to grammars that are very, very simpler with respect to the previous version that didn't support this mechanism. Okay. I don't know if we have any more questions, so thank you very much, and see you around.